As a next talk, we have Svedja from the University of Duisburg, from the chair of Professor Annie, Theoretical Electrotechnic. And he will present some results or some possible workflow with the open source field simulation software OpenEMS. So please, Taro, it's your turn.
Okay. Yeah, welcome to my talk about OpenEMS-based 3D-EM field simulations with the use of complex weighted superposition principle. So it's a bit related to the talk of Mr. Kostov. And okay, it works. So this is the outline of my talk. First of all, I will have some words about OpenEMS. What is OpenEMS? And then show you the concept of this circuit simulation-based superposition, so with theory and a small example. And then I have 3 showcases in OpenEMS, and then make a conclusion. Okay, OpenEMS is basically a 3D electromagnetic field solver, and the great feature is that it is totally open source, so free available. You can simply download it and use it on your PC. It's right now suitable for Linux and Windows, but on Mac it's experimental possible, so maybe you have to try something that it works on your Mac system. Basically it's controlled by a script which you run under MATLAB or Octave. MATLAB is the commercial software which you can use, which is very powerful, and Octave is the open source, let's say, clone, almost. The post-processing you are able to do then directly in MATLAB or Octave. You simply can load in your field data or S parameters and whatsoever. You have it directly inside your controlling script, and so therefore on MATLAB or Octave, and then you can use for field plots third-party thing like ParaView, which is also open source, a very nice viewing tool for VTK and stuff like that, or again MATLAB Octave. So the calculations are based on the EC FDTD scheme. This stands for equivalent circuit finite difference in time domain. So we have a time domain method. Therefore, if we have an excitation with 1 pulse in the time domain, we get directly a broadband solution, if you like to. And almost advantage compared to FEM, the memory consumption of the resources scale linearly with the problem size. In this case, OpenEMS is a bit slower than the, let's say, commercial available tools, but open source. And it has a very simple integration, in this case, of advanced distributed models like Joule models, something like that. And you also are able in OpenEMS to access the code and compute your own fancy features, if you like to. So one feature like this is that OpenEMS is able to calculate not only in Cartesian coordinates, you're also able to calculate fields in cylindrical coordinate systems. So the mesh looks then like this one over here, where the cells are banded according to the cylindrical coordinate system. This is can be quite useful if you have really a cylindrical problem, like a traveling wave scenario, where we got some research in the past. Okay, so the superposition, what we want to do, or what we like to do, as you heard already, we want to replace lump components with ports and then run a full wave simulation, in this case for each port individually, to take the S parameters and the fields and then make a complex weighted field superposition with currents computed by a circuit simulation tool and the S parameters. Okay, for a small example, this is originally presented in this paper here by Carlson. So you have, let's say, this two antenna system, and the first step is to use the first port with an source, and all other ports, in this case the second port, is then terminated by Z0. You simulate everything and you save all the currents, so this error should not appear at this position. But it's Microsoft, so no problem. So you compute these currents, the current you gave into your network, and all the induced current on the other ports. And also you save all your field data, so here maybe the E field and H field. Then you do the same thing again for all other ports. Okay, so we have what we want to calculate now. If we have the currents, we want to calculate an inverse matrix of the current matrix. So in order to, let's say, solve a linear equation system, and then we can calculate by this matrix complex weighting coefficients, this alpha and beta here. So in this case, where we have only two elements, and these Ix and Iy, which we multiply then with the matrix A, are simply the currents at the ports which we get from the circuit simulation tool with our S parameter set. So it's almost, it's actually the same as Mr. Koppel showed already. He made a simulation of his whole antenna system and then takes the S parameter to the circuit simulation tool, calculate there the complex currents Ix and Iy, multiply them with the original or inverse matrix here, and then get these weighting coefficients to make this superposition here. And I have, okay, I have lost the slide over here. So this is the advantage of this technique is that we have fast computation of fields if we have all the data and only change the network. If we make some structural changes, we of course have to simulate it again. But we have a very simple, fast calculation of the total field, so we can make any optimization or worst case scenarios, and therefore it's highly suitable if we have the data for an optimization of, let's say, some capacitors or inductors from our network, so lumped elements. The disadvantage is that we have to do for each port a single simulation. So you can imagine if the simulation of one port takes a long time, then it scales directly with your number of ports. In FTTE or in this OpenEMS here, the simulation time is a bit shorter, or it's much shorter with these terminations. So if you imagine you have a coil which is basically resonant with your capacitors included, or you want to have it resonant at some frequency, but then you replace every capacitor or lumped element with a port which has 50 ohm, then the energy which you put into one port is very fast absorbed in the other ports and in your structure where you have some losses. So basically the simulation time is much smaller compared to the simulation of the structure resonant. And then you have the advantage to make these field superposition and so on. So it's a very nice technique to use for optimizations. So I have so in OpenEMS, this technique is quite simple to implement because we have the access to some script language like MATLAB and Octave. And in OpenEMS itself is also a very simple and small circuit simulation toolbox included, where we have some capacitors, lines, and ABCD metrics which you can define and so on. So you can directly be You don't have to change the program, but you could do this. You could also do the circuit simulation, not in OpenEMS. You can do it in ADS or Cooks or wherever you want. And what you simply need is the current, what you simply need are the currents which are at each single port to then calculate the coefficients you need for the superposition. So if you use it directly with the CTB or the circuit simulation toolbox in OpenEMS, then you have also the advantage to apply all optimization routines which you can program in MATLAB and Octave. So it's very good to use it in OpenEMS, very easy to implement. To show you much more what you can do, so some examples I have here, some showcases. First of all, a single loop coil for the head imaging, let's say, where we want to tune the capacitors of the coil and to design some matching network. So very simple example. Then we take this coil into a 6-channel array and see what are the SARs, what is the SAR if we apply different cases of the phase. And at the end, I will show you a non-circular shaped bird cage where we again want to optimize capacitors. So this is the first showcase we have here, the simple coil and 3 capacitors over here. So it's a standard coil, let's say. And here's the port for feeding. We have a virtual family model with a resolution of 2 mm per voxel. So the edge length is 2 mm. And yeah, this is directly shown with a geometry viewing tool from Console, from OpenEMS, sorry. And what we need are 4 simulations because we have 4 lumped elements, let's say, 3 capacitors and 1 port. And due to FDTD, we can make a broadband simulation just with 1 simulation step. So the simulation is then from 30 to 350 megahertz. And then we are able to tune this simple coil with the capacitors for 3 different nuclei for MRI. So about 298 at 70 to 121 and 79 megahertz in this case. We have the virtual family voxel model of 2 mm size, and on my workstation PC, the simulation time, so I've run it with a 64-bit Linux system and an i7 4790K CPU, blah blah. See all things here. 32 gigabyte memory. Doesn't matter so much, but a single simulation took 7 minutes, and all the simulation together took 28 minutes. But the superposition, including all the circuit simulation and so on, took less than 2 seconds. So it's very highly usable for optimization problems. And yeah, in this case, I simply tune these 3 capacitors to have a resonance structure and then take the real part, which is left by some losses, to an ADS matching tool, Smith chart tool, where I have designed this little matching network composed of an inductor and capacitor to match the 3 cases. So this is all based on the same simulation data, let's say. And then I also had a look to the fields, so not in much detail, I'm not so interested in the fields itself, I just want to show that it works in OpenEMS. So you see basically that the losses are higher in the high frequency, at the high frequency than low frequency. So here's for 1H, here's for 31P, and here for 23 Na, sodium. And the B field or the B1 field, which I calculated, are higher for the lower frequencies. The second showcase is where I put this coil and just place it in a 6-channel array around a head. Again, a virtual family model, but in this case, it's cylindrical coordinates. So all these elements are bent a little bit, as you can see maybe here, according to the cylindrical coordinate system. So it perfectly lies in a alpha range with a specific radius r. Then I've done the same thing again and get for each individual coil some SAR distribution, and can now make a superposition of them with an equal amplitude and equal phase, or in phase, or I can also do it with a CP phase. And you could also imagine to make any optimization to have maybe a worst case scenario for your SAR, what you can get in terms of the phase shifts to for some safety purposes. Okay, and the last showcase is this non-circular shaped birdcage. So we have basically a half circle of as a common birdcage, but the lower part is bent a bit to fit it more to the human body, and also can put it inside the MRI with a patient table. There's not much space in such an MRI, so this is designed for a 7T Siemens system. And in this birdcage, there are 16 capacitors involved, one per rung. So we have to run 16 simulations. It took a while, so we have basically 2.5 hours per single simulation, and therefore 2 times 5 hours times 16, it's about 40 hours for the whole simulation. And then we take all the field data and S parameters again to MATLAB, and then one iteration of the optimization took 1.9 seconds. And the goal for optimization was to achieve a high, let's say, polarization purity, so B1 plus over B1 minus. Here you can see the single ports active, and you see due to the loading of all other ports in, let's say, this simulation here, the field is concentrated mostly on the port which is active. Yeah, with the optimized values, so about 5 minutes we run the whole optimization with, I don't know how many iterations, some thousand. We achieved this distribution here. So the goal was to optimize the capacitor values of this non-circular shaped birdcage. And this is actually now under construction, and we want to test it soon. So hopefully we get the same result as we simulated. So in conclusion, OpenEMS is free and open source, and therefore you can simply download it, use it, and if you like to, you can develop it in your own way. It supports Cartesian and cylindrical coordinate systems. It has all the advantages and disadvantages of the FTTD scheme. So it's time domain based, where you have a broadband solution, but maybe some other disadvantages. You have to use the structured grid and so on. It's controlled by the powerful MATLAB Octave interface, so you can do the post-processing optimization, or even the structure. You can do it with for loops and so on. Very useful. The circuit simulator feature is also included in OpenEMS, so you don't have to change if you have a simple network connected to your antenna setup, let's say. And the circuit simulation based superposition is highly suitable for structural optimization. So the problem is if you make any change of your structure, of course, it's not a change of your lumped elements, and then you have to do the whole simulations again. So if you have different phantoms or whatever, you have to do every time new full wave simulations. But if you only change lumped elements, you can do it in this way very quickly to tune these lumped elements. That's it. Thank you for your attention. And yeah, are there any questions?